every offshore wind turbine ever built can only be planted in shallow water, 80 feet deep or less. But the strongest, steadiest ocean winds blow over deep water. Water so deep you cannot bolt a turbine to the seafloor. A Swedish company thinks they have cracked this problem. Their solution is a floating turbine that assembles flat on the ground, no crane, no specialized vessel, and then gets tipped upright in the water. The Department of Energy says harnessing just 1% of available ocean wind could power 6.5 million American homes. 1%. And right now, we are getting almost none of it. By the end of this video, you are going to understand exactly why deep water wind has been off limits, what this new technology is trying to do about it, and whether it is a genuine breakthrough or a recycled idea that has already failed before. Wind power is having a moment right now. In 2025, wind generated 205 terawatt-hours of electricity globally. That is an 8.2% jump over 2024. Wind is now the second fastest growing source of renewable energy on the planet. It is already keeping the lights on for more than 937 million households worldwide, and almost all of that came from land-based turbines or shallow water offshore installations. Here in the United States, we have barely touched offshore wind. And the deep ocean, where the best winds actually live, has not been touched at all. The reason comes down to one thing. The deeper the water, the harder it is to anchor anything to the bottom. Here at What Happened in Future, and this one, a company called SeaTwirl out of Sweden, is making a move that nobody in the traditional wind industry expected. They are taking a design that has been losing to conventional turbines for decades and betting it is the key to unlocking the deep ocean. Let us look at whether they are right. Point 1. The 3 types of offshore wind and why most of the ocean is off limits. When most people picture a wind turbine, they picture the same thing, a tall white pole, 3 long blades, spinning slowly on the horizon. That design is called a horizontal axis turbine. The blades face into the wind like a propeller. The engine housing sits at the very top, and most of the time, these turbines are bolted directly to the seafloor. That last part is the problem. Fixed-bottom turbines can only be installed in water up to about 60 to 80 feet deep. Beyond that depth, the engineering required to anchor them becomes too expensive and too complicated, so the entire ocean beyond that depth limit has been sitting idle. Now, offshore wind engineers have been working on floating turbines that do not need to touch the bottom. Floating turbines can operate in water depths of 300 feet or more. They are tethered to the seafloor with mooring cables instead of being bolted down, and they export electricity back to shore through underwater cables. This opens up a much larger portion of the ocean. But floating turbines come with their own complications, and that is where the debate gets interesting, because there are 2 very different floating turbine designs, and they do not perform the same way. The first is a floating horizontal axis turbine. Same basic design as the ones you see on land or in shallow water, just sitting on a floating platform instead of being bolted down. These are more aerodynamically efficient, but they have a known problem in the ocean. They fail at a rate 26 to 28% higher than their land-based counterparts. Out in the open ocean, all those moving parts, the pitch systems, the yaw systems, the gearboxes, take a beating, and when something breaks 300 feet out at sea, the repair bill is enormous. The second type is a floating vertical axis turbine. That is what SeaTwirl builds. And this is where the story gets complicated. Point 2. What a vertical axis turbine actually is. A vertical axis turbine works on the same basic principle as every other turbine. Blades catch moving air, that motion turns a drivetrain, and the drivetrain spins a generator to produce electricity. The difference is orientation. In a vertical axis design, the blades run up and down the central post, perpendicular to the ground. The whole assembly spins in a circle around a vertical shaft. No matter which direction the wind is blowing from, the turbine catches it. You do not need to rotate the whole machine to face into the wind the way a horizontal axis turbine does. This means vertical axis turbines have a much simpler mechanical system. No pitch controls, no yaw system, no nacelle rotating at the top of a 100-foot pole. A typical horizontal axis turbine has around 26 sets of bearings. A vertical axis turbine might have 4. Fewer parts mean fewer things that can break. Here is the catch, and it is a significant one. Vertical axis turbines are about 25% less aerodynamically efficient than horizontal axis designs in the same wind conditions. They also need more wind to get started spinning, and there is a structural problem. Because most of the rotating mass is out at the blade tips rather than near the center hub, centrifugal force puts enormous stress on every component as the machine spins. To handle that stress, Every part has to be heavier and more reinforced. The largest vertical axis turbine ever built was a 3.8 megawatt machine called the Eole, installed in Canada in the late 1980s. It was an engineering landmark, and it only operated for 5 years before structural fatigue caused failures severe enough to shut it down permanently. That history is exactly what SeaTwirl has to overcome. And here is the argument they are making, and it actually has some math behind it. Point 3. What SeaTwirl is actually building, and why it is different from what came before. SeaTwirl's design addresses the deep water problem in a way that no horizontal axis floating turbine has been able to match, and it starts before the turbine even hits the water. Their turbines are designed to be assembled flat on the ground in modular sections. No enormous construction crane required, no specialized installation vessel. The individual pieces can be transported, assembled on shore, and then floated out to the installation site. Once positioned, the turbine is tipped upright into its operating position. Conventional offshore wind installation requires some of the most expensive marine equipment on Earth, specialized crane vessels that cost upward of $200,000 per day to operate. You need favorable weather windows, you need calm seas, and you need the whole operation to go exactly right, because one mistake with a component that big is a catastrophic problem. SeaTwirl's flat pack approach, if it works at scale, could meaningfully reduce those upfront installation costs. The turbine sits on what engineers call a spar foundation. Picture a long cylindrical buoy, partially submerged beneath the surface. The deep submerged section makes the whole structure far more stable in rough seas. Waves and currents that would rock a surface-mounted platform do not affect the spar nearly as much. And SeaTwirl's generator, instead of being housed at the top of a 100-foot pole like a conventional turbine, is located at sea level, which means maintenance workers do not need a cage elevator or a helicopter drop-off to reach it. That matters a lot when you are talking about a turbine sitting in the North Sea in February. A Japanese research study comparing floating vertical axis turbines with floating horizontal axis turbines found that vertical axis designs came out about 3.7% cheaper per unit of energy produced. 140 euros per megawatt hour versus 145 for horizontal axis. If they can back that up with data, that is genuinely competitive. The word "if" is doing a lot of work in that sentence. Here is what the real-world track record actually shows. Point 4. SeaTwirl's real-world track record so far, and why it is both promising and incomplete. SeaTwirl installed their first prototype, a 30-kilowatt unit called the S1, off the coast of Sweden back in 2015. That is over a decade ago, and it is still in the water. It has survived hurricane-force winds and brutal North Sea winter storms. It is connected to the grid and generating power. That is genuinely impressive for a floating vertical axis design. The history of this technology is littered with machines that did not survive their first serious storm season. But beyond that single prototype, the progress has been slower than expected. SeaTwirl's next planned deployment was a 1-megawatt test unit called the S2X. The target installation date was 2020, but in 2026, 6 years later, the testing authority withdrew the license before the turbine ever entered the water. The stated reason was changes in the project framework. The planned test site was a fish farm in relatively sheltered water, not open ocean, so that data gap still exists. SeaTwirl then secured funding from Horizon Europe, a major European Union research grant, to deploy a 2-megawatt demonstration project called Vertigo. That project is scheduled to run through the end of September 2029, and they moved straight from the 30-kilowatt S1 to the 2-megawatt Vertigo, skipping the 1-megawatt intermediate test entirely. That is a 66-fold jump in scale, from 30 kilowatts to 2 megawatts, without the intermediate data that the S2X would have provided. That is not unusual in energy technology development, but it does mean there are questions that will not be answered until 2029 at the earliest. SeaTwirl has previously claimed their design delivers 20% lower costs than conventional floating horizontal axis turbines, but they have no publicly available cost data from the S1 deployment to back that number up. That claim is projection, and in the energy industry, projections have a long history of not surviving contact with full-scale deployment. Point 5, where this could actually matter for American energy, and what still has to be proven. Here in the United States, we have something that makes deep-water floating wind turbines especially interesting, and that is geography. The Atlantic coast and parts of the Pacific coast drop off into deep water relatively close to shore. That means floating turbines could be positioned where the strongest winds blow, and still be close enough to shore to export electricity through undersea cables at a realistic cost. The Department of Energy has estimated that offshore wind could supply a massive share of American electricity demand. But most of the best deep water sites are currently locked out of development because fixed-bottom turbines cannot reach them, and floating horizontal axis turbines cost too much to maintain in those exposed ocean conditions. SeaTwirl is also targeting a market that has almost nothing to do with powering American homes directly, at least not yet. Oil rigs in deep water currently run on diesel generators. They consume enormous amounts of fuel just to power their own operations. SeaTwirl has identified this as a potential early market, selling electricity to platforms that already exist in deep water, right where their turbines are designed to operate. The same logic applies to isolated island communities and remote coastal installations, places that currently pay extremely high prices for diesel-generated electricity and have no realistic path to a grid connection. These niche applications are not as headline-grabbing as powering 6.5 million American homes. But they matter. They are the kind of real-world deployments that generate actual operational data, the data that SeaTwirl currently does not have and desperately needs. The honest assessment is this: SeaTwirl's core engineering argument is sound. In offshore environments, where maintenance costs dominate the total lifetime cost of a wind farm, a simpler machine with fewer failure points has a real structural advantage. The 25% efficiency deficit of vertical axis turbines versus horizontal axis designs may be genuinely worth trading in exchange for dramatically lower maintenance costs when you are 300 feet out at sea in winter. But sound engineering arguments and delivered results are two different things. The S2X never got in the water. The Vertigo project will not produce results until 2029, and the jump from 30 kilowatts to 2 megawatts is a significant scaling leap with an unknown outcome. The history of vertical axis wind turbines is full of designs that worked beautifully at small scale and fell apart at large scale. SeaTwirl needs to prove they have solved the fatigue and structural stress problems that killed the Eolay turbine in Canada 4 decades ago. Here is where we land on this. Wind power is growing faster than almost any energy source on Earth right now, and the biggest untapped reservoir of wind energy, deep ocean water, is still sitting completely idle. Not because the physics do not work, but because the engineering challenge of getting into deep water affordably has not been solved yet. SeaTwirl is making a real argument. Simpler mechanical systems, flat pack assembly, sea-level maintenance access, lower projected lifetime costs, and one prototype that has genuinely survived over a decade in the North Sea. But they are also working against 100 years of vertical axis turbine history that says scaling up is where these designs tend to break. The Vertigo project, their 2-megawatt demonstration, will be the most important test of whether that history repeats itself or gets rewritten. You now understand something that most people following the energy conversation do not. The fight for deep water wind is not just about bigger turbines or more money. It is about which fundamental design, horizontal or vertical, can survive the real-world punishment of the open ocean at a price that actually makes sense. And that question is still open. This technology could realistically contribute to reducing American electricity costs by expanding the total supply of wind-generated power. More supply from deep water offshore sites means less pressure on the grid and less pressure on your bill. Here is my question for you, and I want to know what you actually think. If SeaTwirl's Vertigo project delivers the cost and performance numbers they are claiming by 2029, would that be enough to convince you deep water floating wind is for real? Or do you think horizontal axis floating turbines will solve the maintenance problem first and make vertical axis designs irrelevant? Drop your answer in the comments. Tell me what state you are in, because your coastline and your power costs matter when it comes to how this plays out for you personally. I read every single comment, and if you are curious about energy technologies that are already working right now, not waiting on a 2029 test result, I have got a video that covers a system you can build this weekend for under $40. No ocean required. It is right here. If you want to stay ahead of the energy technologies that are actually going to change what American homeowners pay for power, subscribing to What Happened in Future is the best way to make sure you do not miss what is coming next. The deep ocean has been sitting there, full of wind energy, for all of human history. The only thing missing was a machine that could survive out there long enough to make it worthwhile. Whether SeaTwirl is that machine, we will know by 2029. I will see you in the next one.